In the last video, we talked about Alfred Wegener and his theory of continental drift. And it was a really pretty good theory, and he had really 5 good pieces of evidence, but he could not come up with a good mechanism for allowing these continents to plow through the oceans. Because of that, not a lot of people believed him. He was kind of ridiculed. He goes back to Greenland, dies of a heart attack on the ice up there, with a lot of people kind of forgetting he even had this idea. Also, a world war gets in the way, and all of a sudden, people aren't concerned with why continents are moving. They're more concerned with fighting the Axis or the Allies and winning the war. And we usually think of wars as really bad things for people, which they are, but they're really, really good for technology. So we're going to talk about some of this technology that then leads to the next piece and a better mechanism. So this is kind of a long lesson. We're kind of really finishing up the idea of plate tectonics in just one last lesson here. So we're going to go through it really quickly. It may be a little complicated. I may leave some things out, but that's okay. You can come talk with me about that. This is really just a brief overview. As I said, the war starts, and a lot of new technology is developed. One of the new pieces of technology is sonar, and with it, the fathometer. And one of the captains of one of the ships was also a geologist named from Princeton University named Harry Hess. And what he decided to do is, instead of just using his fathometer when he needed it, like going around the island of Iwo Jima, he decided to turn his fathometer on all the time when he was crossing the oceans. And when he did this, what he found was the ocean floor was not flat, as many people believed it would be. He found instead that there's a mountain range over 16,000 miles long that connects all the oceans. And that mountain range is called a mid-ocean ridge, or there are multiple mid-ocean ridges. For example, the Mid-Atlantic Ridge or the Mid-Indian Ridge. So you see the Mid-Atlantic Ridge right here in the middle of the Atlantic Ocean, Mid-Indian Ridge here in the middle of the Indian Ocean. This is the East Pacific Rise because it's not in the middle, it's in the east of the Pacific. But these mid-ocean ridges all connect to form the 16,000-mile mountain range. In the middle of each ridge is a V-shaped valley called a valley. We'll draw it here in a second, but basically the top of this, there's a V-shaped valley. And they're going to find that instead of the ocean water getting colder with depth, as they expected for all the oceans, the ocean water actually got hotter with depth in the valleys. We'll show you that too. At the edges of the ridges by the continents, there are trenches, which are the deepest parts of the ocean. So real quick, we're going to have you draw a picture of what the ocean floor looks like. So again, very simplified view. So we're going to say that there's a continent over here and a continent over here. So then the ocean is going here, so just putting this at the top of the water, so kind of messy drawing. There's just the ocean there. So what we found was by the continents, after the continental shelf, it gets really deep. And then it gradually works its way up, this is the ocean floor, until in the middle of the ocean, there's this V-shaped valley, and then the ocean floor goes down the other side. So again, a lot of people believe that the ocean floor was flat. What Harry Hess finds is it's not flat. There's this huge mountain in the middle of it. So this whole big mountain they called a mid-ocean ridge. The valley at the top is called a valley. And the trenches in the side here are called trenches. Very simple language. And as I said, after they found this new feature, they wanted to investigate it. And one of the easiest things they could do was find the temperature. So they would go along, kind of starting at the continents, and they'd have their boat or their ship, and they'd drop down their thermometer, and they'd measure the temperature as they went down. And as they expected, the temperature got colder with depth. Go down over here, colder with depth. Over here, colder with depth. When they got into the valleys, it actually got warmer with depth until the water at the bottom of the valleys was boiling. It was so hot. And then back over here, colder with depth, colder with depth, colder with depth. So that was new for some people. But that's going to help Hess come up with this better mechanism as to why the continents are going to move, or really the seafloor spread, as he's going to say. So Hess is going to come up with this idea called seafloor spreading. And it's just a better mechanism than Wegener had. So what he says is there are convection cells in the asthenosphere which cause the seafloor to spread as rising magma pushes and pulls the continents apart. Thus, new ocean floors created the valleys, while old ocean floors recycled at the trenches. Okay, so a lot going on in this explanation, maybe some new terms too, because we didn't talk about them yet. A convection cell first, that's just a circulation of a heated fluid. So basically, if you have heat in one spot, let's say down here, you think of hot air, hot magma, whatever it might be, is going to rise because it's less dense, hit the top, spread out, cool, and fall, and make a cycle going around and around and around. Okay, works with air, works with water, works with whatever fluid. So it's a convection cell. So he says there are convection cells, the cycling of a fluid, in the asthenosphere. Okay, what's the asthenosphere? We haven't gone over that yet. Basically, think about the parts of the Earth. The middle of the Earth is the core. You should know that. Core has an outer core and an inner core. There's the core. The next layer out from the core is the mantle. The mantle is actually split into 3 sublayers. We're only going to really talk about 2 of them. This rigid or a hard outer part of the mantle, and then a plastic next layer, kind of middle of the mantle. Now, that word plastic, that just means a slowly flowing fluid. Think of it like a really thick peanut butter, so really slowly flowing fluid. So the top of the mantle is hard. The crust, of course, is hard. So the crust and upper mantle are stuck together. They're like welded together. So instead of talking about just the crust as the hard outer part, we're going to talk about the lithosphere. So you see it here, lithosphere is that hard outer part, the crust and upper mantle. The asthenosphere is that slowly flowing layer, that plastic layer. So that's that really thick magma that's going to have the asthenospheres. So what Hess says is that we have magma in the asthenosphere. It's going to get hot because there's going to be some hot spikes in the core. It's going to rise up, hit the underside of the lithosphere, spread out, and as it spreads out to either side, maybe I can do it here, kind of imagine this is the valley with mid-ocean ridge. Got the core down here. So this hot magma is going to rise up, hit the underside of the lithosphere, and it's going to spread out. It's going to cool and dive back down to be reheated again. Okay, so these are convection cells. So what's happening is this piece of lithosphere here, maybe you can imagine that this is part of South America plate. This is the African plate. So as it slides to either side underneath, it's going to pull these apart, these 2 plates apart. What's going to happen is then you could get a little bit of magma coming out of the middle here, a little volcano coming out of the middle there, and that would boil the water, making that heat flow data that really, really hot in the middle. So as these cycled around, it would split the seafloor and thus move the continents. So this is a much better mechanism than what Wegener had. Okay, it's easy to figure out that we could see that there's these circulations of magma underneath the continents or the seafloor that would kind of push and pull them apart. So the old ocean floor is going to be down here in the trenches, and the new created in the valleys. Well, we need more evidence for this, of course. We have a new theory. We have to have more evidence. I'm going to go through this evidence really, really quickly. First piece of evidence is the age of the ocean floor. The age of the ocean floor, it is the oldest in the trenches and the youngest in the valleys. So the valleys, right in the middle, kind of where that heat flow was, it's brand new rock right now, okay, forming right now. As we get out going older, in those trenches, it's about 180 million years old. So it's youngest in the valleys, older towards the trenches. The age of the ocean floor is also symmetrical. So if I pick a piece of rock over here, ocean floor, and I pick one the same distance away from the valley over here, what we find is that they're the exact same age. So essentially what you could do if you had a continent here and a continent here, again, say South America maybe, and Africa, you could work back line by line by line, and Pangea would reform on the valley. They also found that the ocean floor is younger than the continents, again, leading to this idea that the ocean floor is recycled. Where the continents are billions of years old, the ocean floor was only about 180 million years old because it's constantly being recycled in these convection cells. They also found paleomagnetic data, which is basically the magnetism of rocks. The polarity of the ocean floor is symmetrical on either side of the valley, and the magnetism on rocks on land shows they've moved. Okay, so again, we're going to go through this really, really quickly. Imagine you have a volcano. The volcano erupts lava. In that lava, there is little filaments of iron. Before that lava can harden, the filaments of iron have time to point themselves to where the North Pole is. So if you look at these rocks that are now hardened, you can see these little pieces of iron pointing to where the North Pole was. So now if we look at, go to the continents, we can see that those little filaments of iron no longer point to where the North Pole was, so it leads us to believe that the continents have moved. Also in the oceans, we see these zebra stripes of polarity. So basically the iron pointing north or the iron pointing south. But again, the key is they are symmetrical on either side. That was a really, really quick summary. I've got a whole 20-minute video on paleomagnetism and how it happens that you can watch if you want more information on it. But basically, the idea is that by looking at the magnetism in the rocks, we can see that the ocean floor spreads symmetrically to either side, and we can see that the continents have moved as well. Some other evidence, we see that some islands and island chains are lined up by increasing age. You look at Hawaii, for example. The Hawaiian Islands kind of here, they get older in this direction and smaller. The newest island of Hawaii is the biggest one here. So basically what happens is the lava comes out. We'll talk about this in our next unit, volcano unit. Lava is going to erupt. It's going to make an island. Maybe you can see up here. So lava erupts. It makes an island. The plate is going to drag it that way. So all these islands are older and then smaller because they're away from this hot spot that's creating them. Also, we see pictures like this. We see earthquakes and volcanoes. So these, the red and the black, these are all earthquakes. So you can see these earthquakes outline where the plates are, showing that, yes, there are plates of lithosphere. They're floating on the asthenosphere, and they're going to be bumping into each other, moving next to each other, creating earthquakes and volcanoes. This map up here, I didn't show this. This is just, again, the age of the rocks. The red being brand new, and then the dark blue being the oldest. So you can see, again, that in the middle of the valleys, we are brand new rocks, whereas on the edges of the continents, it's the oldest. So again, you could go back line by line by line and reform Pangaea. You could take these zebra stripes of polarity of magnetism and again go back line by line by line by line and reform Pangaea. So it's all just good evidence to show that Pangaea did exist, and now the continents, or really the plates, are moving apart. So I think really the last thing is we get back to our explanation or our definition of plate tectonics. This is what we had on the first slide there. So plate tectonics theory says the Earth's surface, the lithosphere, we talked about that, is broken into pieces called plates. We just talked about that. The plates float on the asthenosphere, we talked about that, and move because of seafloor spreading. We went through that and some evidence for it. They either move into each other, creating a convergent boundary, away from each other, creating a divergent boundary, or slide next to each other, creating a transform boundary. So the only thing we have left to talk about are these three boundaries really quickly. And this is kind of why we really need to do this unit. When we start talking about volcanoes in our next unit and then earthquakes in the unit after that, these are the reasons for earthquakes and volcanoes. So that's why we couldn't just kind of ignore this plate tectonics unit. We had to cover it, even if we cover it quickly, because we need to know this information for earthquakes and volcanoes. So we said there are three different types of boundaries. Divergent boundary. Plates move away from each other. So if I did like just a simple picture, if I had kind of a plate here and a plate here, I draw an arrow. The plates move away from each other. Simple. We're going to get the mid-ocean ridges. We're going to get oceans. The valley is right there in the middle. We're going to get some small, shallow earthquakes from that. We're also going to get rift volcanoes. That might be a new kind of term for you, Basically, a rift volcano is a crack with lava flowing out. So you see, as the plates slide apart, lava can spit out of here, and it makes a rift volcano. One of the best examples, so you look at kind of our map for examples of these, Iceland is a great example right up here. So we can see here, half of Iceland is on the North American plate, moving towards the west. Half is on the Eurasian plate, moving towards the east. So Iceland literally gets ripped in half. As it rips in half, there are volcanoes here with lava flowing out. Here's a picture of this rift valley in Iceland. So there's not lava coming out right this moment, but there will be more. But you see basically North America on one side, Eurasia on the other side, and this valley in the middle where it's getting ripped apart. So we have these rift volcanoes, we have some earthquakes, but they're shallow, not very strong earthquakes. A transform boundary is where the plates slide next to each other. So think if you had an overhead picture, maybe you have your two plates and one of them is moving this way and one of them is moving this way. So that'd be like a top view of that. We don't get volcanoes. We don't really get a whole lot of other stuff. We get lots of earthquakes with this. Your best example for this one, they don't really have it on the map here, but down here is the San Andreas Fault in California. So when we look at that, what we have is the North American plate is mostly going kind of to the west, whereas the Pacific plate is kind of sliding up to the northwest. So at this boundary, the two plates are rubbing against each other. When the two plates rub against each other, they make earthquakes. Again, we'll talk a lot more about this with our earthquake unit. You see a farmer's field here. The fault is kind of right in the middle here. You can see one side of the fault is going one way, the other side is going the other way. And it creates earthquakes and it deforms the surface there. The last type of boundary is a convergent boundary, so it's plates that move toward each other. And there are kind of three subtypes for this. So we're just going to go through them really quickly. Continent to continent. So I have a continent plate smashing into a continent plate. What happens is I have this big, thick, not very dense continent smashing into another big, thick, not very dense continent. What happens is the land gets pushed up and it makes big fold mountains. These are not volcanic. And it also makes medium to shallow earthquakes. Great example of this are the Himalayan mountains. So India, again, because of plate tectonics, India is cruising up here to the north and smashing into Eurasia. And when it smashes in, it makes these big folded mountains. The next type is ocean-ocean convergence. So ocean plates are thin and very dense, made of basalt. Let me do that a little bit differently. Let me do it over here. So we have this one going like this. And then when these two thin plates come together, one of them is going to dive beneath the other one. That's called subduction, when one plate goes underneath another one. So it makes this subduction zone. What happens, this plate here, now it goes down into the asthenosphere, so it melts. Lava goes up and makes a volcano. So these are volcanoes in the ocean, so they're islands, and they're in the shape of an arc, so we call them island arc volcanoes. You're also going to get trench right here, and you can also make tsunamis with this, and we'll talk more about tsunamis later, but this is where we get tsunamis. Some good examples of this, the Aleutian Islands here in Alaska, Japan is a great example of this, where we have these island arc volcanoes. And then the last of the three types of convergent boundaries is ocean-continent. So now we have a big, thick, not very dense ocean plate coming together with a thin, dense ocean plate. The ocean plate is going to subduct underneath the continental plate. As it does, it's going to make a trench here, of course. It's going to melt, go up, and make big, violent volcanoes. So we're talking about the violent volcanoes that are formed here. So we have volcanoes, earthquakes all along here, big, small, deep, shallow, and trenches here. Good example of this, you could have it as the Andes Mountains here, where the Nazca plate is subducting underneath the South American. Also, up here in North America, we have the Juan de Fuca plate subducting underneath the North American plate, making Mount Rainier, Mount St. Helens, all those violent volcanoes up on the northwest coast of the United States. And then this just last thing is just a little picture, again showing kind of what maybe 65 million years ago looked like. The continents have moved to present day, and then this an interpretation of maybe what would happen in the future. And you see some things like separating here. Baja California has slid up farther. A little piece of California has gone with it, maybe a little split here. Some of these islands have connected here. But really, kind of we go back to this original idea of what plate tectonics is the Earth's surface is split into big pieces called plates. They're floating on the asthenosphere, and they're moving because of seafloor spreading, those convection cells underneath them. And they're bumping into each other, going away from each other, sliding next to each other, and that's going to create the earthquakes and the volcanoes that we're talking about in our next unit. Thank you.